Hello, everyone. In physics, as well as in math, we found that a lot of different coordinate systems are very helpful. So I'm going to introduce three videos. The first one will be on Cartesian coordinates. The second one's going to be on cylindrical coordinates, which is basically polar coordinates, but in 3 dimensions. And then the third one will be on spherical coordinates. I'm going to do so by introducing not only the coordinates, but I'm also going to introduce the unit vectors, I hat, j hat, and k hat in the case of Cartesian, as well as different surface areas, dA, and expressed as vectors, and differential volume elements. So let us get started with the Cartesian coordinate ones right now. So let's turn over to the document cam. I've already taken the time to draw the Cartesian coordinate system so it'll be a little neater. One thing you need to know is you can't just haphazardly draw X, Y, and Z in any general directions. Generally speaking, when you go to draw X, Y, and Z axes, they have to be obeying the right-hand rule. So what that means is if you lay your right index finger pointing like this, and notice my middle finger is pointing that way perpendicular to my index finger, and then my thumb is pointing perpendicular to both of them up. If you do this with your right hand, you're supposed to have your index finger along the direction of the x-axis with your middle finger along the direction of the y-axis, and when you do that, the z has to be in the direction of that thumb. This actually matches that coordinate system. If you don't do that, your cross products and determinants and matrices, all sorts of weird stuff come out kind of funny. So just always make sure you make your coordinate system right-handed using that x-axis, y-axis, z-axis, and pointing in the positive directions in all cases. So first off, in this x, y, z coordinate system, we have our unit vectors, which you might remember as I, j, and k. You can also use x hat, y hat, and j hat. So if we imagine a vector that's exactly 1 unit long, pointing along the x-axis, that vector is called I hat. And the hat indicates basically almost universally that you're talking about a vector whose magnitude is 1. And I mean exactly 1. I don't mean 1 meter or anything like that. In fact, the way you find a unit vector pointing in any certain direction, you just take 2 points in the direction that you wish to make the vector, and you subtract the final point minus the initial point. So x2 minus x1 would be the x component, y2 minus y1 would be the y component, and z2 minus z1 would be the z component. You then have a vector whose length is x2 minus x1 squared, or square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. That would be the magnitude. But to make a unit vector, you then divide it by that magnitude. So you end up getting, say, meters in the top and then meters in the bottom, so it actually has no unit. So remember, a unit vector is literally a unit long, okay? Now, the other ones are the j hat. By the way, that's also x hat here. I hat is also x hat. There's also the j hat vector, which is also supposed to be 1 unit long. It looks a little longer here because that one's not pointing out of the page like the x-axis is supposed to be. That one's called j hat, and it's the same thing as the y hat vector. And then finally, there's another one that's 1 unit long, pointing along the z-axis in the positive z direction, of course, and that is k hat, which we also sometimes write as z hat. Most teachers will allow either one. Sometimes people just use x hat, y hat, and z hat just because they can't remember which one was I, j, and k. They both follow the alphabet, though, so it should be pretty straightforward. Now, let's talk about coordinates, or excuse me, differential area elements. Let's imagine that we're at a position x, and then we allow it to vary by an amount dx, so that this is x plus dx. So we have x here, and we have x plus dx there. So that actually makes a range of x values, which I'll represent this way. So all the points with values between x and x plus dx are in this little box, and of course it goes infinitely far that way, infinitely far that way. Now if I imagine the y-axis stuff experiencing a similar change, then maybe this would be y and this would be y plus dy. So then I'd have this here, and this is y, and then this would be y plus dy. So I'd put another one. I'm trying to draw these parallel to that, so it looks like it's actually in 3 dimensions like it's supposed to. So you can see now I have a little area of element, a little area element that we can call dA. And I'll say that's dA sub xy just to give it a name. And we normally indicate it as a vector. Now, the problem is we always choose the vector to be perpendicular to the actual area element. So that means it either needs to point in the z direction or the negative z directions. Either one's acceptable. Sometimes when you're using these area elements, there's a convention where, for instance, you're talking about integrating over a closed surface, a surface that has a clear inside and outside, then the dA vector is supposed to be pointing out. But in this case, you have no, it's pretty ambiguous which way you put. So I'm going to write it as plus or minus. But notice the area is dy. It's sort of a rectangle, so, or it's definitely a rectangle. So this width is dy and this width is dx. So it's dx, dy, and then the plus or minus gave me for the direction k hat, which you could also write, as I said before, as z hat. What if instead you chose to allow y and y plus dy to change, y to change to y and y plus dy, right? But instead of letting x change, you only decided to let the other variable change be z. If that's the case, then you're going to get a value z, say, that's right here, and a value z plus dz is right here. So you get another area element. That one will be dA. Let's call it yz. Again, it's going to have a plus or minus because the direction's arbitrary, but we know it's got to be perpendicular. So that's in the yz plane, which means perpendicular to it is pointing in or out. So that's the x hat or the I hat direction. So this one's going to be dy dz, and it will be in the x hat direction or I hat direction. So I'll put the vector symbol on it, and I'll say this is in the I hat direction. Again, the plus or minus dictates whether it comes out or goes in. Now, finally, we've done x and y, and we've done y and z, but we haven't done x and z. So if we let x vary and z vary, then we'll get yet another area, and in that case, it's over here. So I draw, first off, I'll draw the z's, so we can get an idea of roughly where it's supposed to be. I'm trying to make this parallel to the z-axis as best I can, or excuse me, to the x-axis as best I can, so it'll look nice and authentic. And do the same thing here. And now this has got to be parallel to the z-axis. So now I have an area element right here that I'll call dA xz. Okay. Obviously, that has a height dz and a width dx. So I'm going to call it plus or minus dx dz. And of course, it points in the plus or minus j hat direction. So that's your 3 area elements that you can get in Cartesian coordinates. If you actually combine all these, you'll get an actual volume element, which I can do by this. Let's do this vector right here. Actually, let me switch colors a little bit, make it maybe a little bit easier to see. Okay, let's see over here. Okay, now I'm going to draw this one coming up here and this one coming up here. And you see finally I get a little rectangular solid up here whose dimensions are dz, dy, and dx. So that differential volume element, dv, is equal to dx, dy, dz, and we haven't found any reason to make that into a vector, so that's just fine the way it is. But now we have a three-dimensional representation. Notice this is supposed to be just a continuance of this line right here, and so on and so forth. This is supposed to just be a continuance of this line right here. And of course, this would be inside of there, inside of there. So you hopefully can see now that's a three-dimensional body. So I think with all that, you get an idea. Now, the beauty of using these is you can do volumes really easily, like you did in Calc 2, where you had like to use disks and washers and stuff like that. But with this case, you just use a differential volume element and integrate that. But the downside is you're using a triple integral, and that seems scary to people. So I can say the volume of a cube is the integral of the differential volume, which would be the integral from, let's say, x equal, or let's say z equals a to b, and then y equals c to d. So what I want to try to do is picture a rectangular solid. This one would be at a and b, and then the y, which was going this way, would be at c and d, like that. So now I got the rectangle, but not the solid part. And then, of course, this would be the ultimate rectangle that we're talking about. And of course, this would be at, let's say, x equals e to x equals f. So I think you can tell just looking at this diagram, the volume should be e minus f times c minus d times a minus b. So now I'll do this integrals. The integral of x from x equals e to x equals f, and the volume element would be dx, dy, dz, and I treat it like the innermost one hits the first integral. The integral of dx is just x, and that's evaluated at e and f, so I end up doing f minus e. So I get f minus e times the double integral, z equals a to b, y equals c to d of dy dz. Of course, the integral of dy is just y evaluated from d to c. So the integral of y evaluated from d to c, being y, is just d minus c. So now I have f minus e times d minus c times the integral of dz from z equals a to b. So now I finally have f minus e times d minus c. Whoa. And integral of dz is just z evaluated from b to a, so that'll be b minus a. So you can see, you could call this one say length, this one say width, and this one say height, and you did in fact find that the volume of a rectangular solid is in fact length times width times height. So that's one of the many advantages, of course, you can see to using these coordinate systems and their little unit vectors and all that good stuff. You haven't actually seen a use for the unit vectors being on the DAs yet, but that will come with your physics and our calculus courses. So that's the end for Cartesian coordinates. The next video will be on cylindrical coordinates.